Alrighty, howdy folks. So let's move on to chapter 6. This is completely different, luckily. Um, I don't know why I said that. Anyway, internal rate of return. Okay, rate of return, that's the chapter 6. And section 1 is something called internal rate of return. Next section we'll do external rate of return. Okay. Uh, I will tell you that internal rate of return is a very, very popular one. A lot of people in the finance and the management and all of that, they use this particular number. Internal. What's the internal rate of return? They would say. Okay, what is it? Definition. The internal rate of return, IRR, is the interest rate that makes the present worth, the future worth, and the annual worth equal to zero. In a way, that's kind of redundant. The moment the present worth of something is zero, automatically the future worth is going to be zero and the annual worth would also be zero. So the thing is, the reason it is being stated that way is depends. So whatever is convenient for you, calculating the present worth is convenient for you. You somehow know those formulas much better than you know the formulas for the other ones. Go ahead, use a present worth formula and set that equal to zero. Okay. And you can do, or you can do future worth or the annual worth. Any one of those things would work. And it is also referred to as the discounted cash flow rate of return, the cash flow rate of return, or just simply the rate of return ROR. This is a very common one. Rate of return. What's the rate of return? What is the rate of return? They keep asking. Or the return on investment, ROI. This is also a very commonly used term. And true rate of return. I don't know. I don't think I ever heard true rate of return. Anyway, importantly, if the internal rate of return, IRR, is greater than the minimum attractive rate of return, the investment must be made. Just see if that makes any sense to you. So you have a project which has a certain cash flow, meaning you'd be spending some money, you'd be gaining some money, and maybe in the end you have some salvage value, whatever, right? And you are figuring out what rate of return, what interest rate, in fact, would cause all of this cash flow to give you a zero present worth. Meaning, zero means if you make this much, if you earn this much interest rate, good, you have broken even, right? So, what is that minimum thing? Is what you are saying. And that is the internal rate of return. Now, would you agree that if that minimum interest rate that your project earns is greater than or equal to your minimum attractive rate of return, you should make that investment? If you don't make that investment, you will be merely earning the minimum attractive rate of return. And apparently now you are going to make definitely something more than that minimum attractive rate of return. So it stands to reason you would make the investment. Right. All right. In addition, IRR is not a ranking method. That is, if the IRR of option A is greater than IRR of option B, then it is not automatically the case that option A should be chosen. Why not? The internal rate of return is bigger, man, for option A, so why shouldn't I pick it over B? That's because the initial investment of each option may be different. What? The initial option may be different. What does it mean? Check this out. Suppose somebody tells you, hey, if you invest $1,000, your friend comes to you and says, if you give me $1,000, I tell you what, in a year from now, I'll give you $1,200 back, right? And you quickly calculate, so 1,000 gives me 1,200, so that is 20% interest, internal rate of return is therefore 20% for you. Good. But then the friend says, however, if you give me $100,000, I'll give you $150,000 back. And you quickly calculate how much the internal rate of return for that is. So that is 50%. So the first one was 20%. This second one, the $100,000 investment thing, is 50%. So should you automatically pick the one that's giving you the higher internal rate of return, the 50%? No, because not necessarily. Not necessarily because $100,000. If something goes wrong, God forbid, then you are in the negative quite a bit more. So there is risk associated with a bigger investment, right? So you may still do it if your friend is so reliable that you want to take that option, that's fine. But it is not automatically the case that whichever has higher internal rate of return should automatically be picked. That's all that statement is saying, and for the reason I said. Cool. IRR is the second most popular investment strategy for the investors after present worth. Uh, okay, I did not know that, but kind of makes sense in a way when you think about it. Okay, let's see some. There are some very interesting things in this section. Really, you really need to pay attention. Okay, cool. Internal rate of return for a single alternative. There's only one thing. You either do it, you do this project, of course. Even though it's a single alternative, there is always a second or default alternative. Would you agree? What is that? The do nothing one. Okay, so for a single alternative, let's consider the following cash flow diagram. What's the value of X if the internal rate of return is 15%? What's the value of X if internal rate of return is 15%? Aha, so you mean for what value of X and this rate of return of 15% or the interest rate of 15%, the present worth of this whole cash flow would be zero. Or equivalently, the future worth of all of this cash flow is zero. Yes, that's the whole idea. Cool. Since we are given that IRR is 15%, we will set the future worth equals zero and find X. Future worth, project this guy forward to 2 years by multiplying by 1 plus 0.15 square. Use the internal rate of return 0.15 for this. And then the future worth of those two uniform series ones would be X times 1 plus 0.15 square minus 1 over 0.15. Right? Present worth would have another 1 plus 0.15 square in the denominator, but since we are looking at the future, we won't have that in the denominator. And now it's just a matter of solving for X, right? A simple calculation. And that turns out to be $246.05. Cool? Good. That's a nice simple problem to get our feet wet. That's a good American expression, right? Let's get our feet wet. I tell you, I could speak English back in India even before I came to America. But I mean, the number of expressions, the what? Let's get our feet wet. What in the world does it mean? Oh man, this guy came by my house and I was sweating bullets. You are what? Sweating bullets. Dang, what in the world is that? Right? But then you get used to it. Anyways, what's the IRR of the following cash flow diagram? Oh, nice. Another nice simple problem. to not just get a feet wet, we already got our feet wet, so let's go into a little depth, right? Solution. To find the IRR, we'll set the future worth equals 0 and solve for I. Future worth is we got to project this 30 guy all the way up to t equals 3. And so it's since it's negative, we say negative 30 times 1 plus I, the quantity cube, and continue the negative 15, 1 plus I square, positive 30 times 1 plus I plus 31. All of that should equal 0, right? And what are we trying to do? We are planning to find the value of I. Aha, good. So how do we do this? Oh my, that's a cubic polynomial in 1 plus I, right? Oh, that we don't know how to solve cubic polynomials. That I mean, there we do, but they are not so straightforward. So guess what? You just have to use trial and error or use some software to figure this out. So what I have done is I set x equals 1 plus I. That made it into a minus 30x cube plus 15x square plus 30 blah blah. And then, figured out what the value of x is. And then I figured out what I is. I used Excel. Or maybe I may have used GeoGebra to draw this polynomial and looked at where the roots were. Yeah, cool. And yeah, I did do GeoGebra. And then I saw that when I draw this graph, x would be 1.15. X, not I. Okay, x is 1.15. Oh, but x itself is 1 plus I. So 1 plus I is 1.15. And so I is 0.15 is 15%. Cool. Simple, straightforward. Um, Wait. What? Oh, what, what's that American expression? Not so fast, Jose. Not so fast, Jose. Who the hell is Jose? Whoever that guy is. Not so fast, Jose. Why not? What? So the thing is, yes, we found a certain value for x, right? But notice this is a cubic polynomial. So a cubic polynomial should have 3 roots, right? So there should be 3 values of x that would satisfy this equation negative 30 x cubed minus 15 x squared and so on. 3 values. But all I picked is x equals 1.15, right? So the truth is there could be more than one value of I that would satisfy the equation here. And that is the next concept that we are going to look at. How do we know? Yeah, maybe I should put it this way. However, in this case, I know something, and based on what I know that I need not worry about the other 2 roots. The fact that I got x equals 1.15 and I ran with it is perfectly fine. Okay. And the other 2 roots, I don't have to worry about that, about them, even though they do exist. What? Why not, man? Yeah, I'll tell you. Cool. IRR calculations, multiple roots. This is exactly what I was alluding to in the last slide. Okay, consider a cash flow diagram as shown. There's a P, investment P, there's further investment A1 at T equals 1, and you start getting money at A2, A3 at 2 and 3 years. And so, what's the IRR? Okay, same standard thing. Minus p times 1 plus I, the quantity 1 plus I cube, minus a1 times the quantity 1 plus I square, blah, blah, all of this, kind of exactly like that. Now, this is what I would rather just say x equals 1 plus I, so that now that looks like a familiar math thing, a third degree polynomial or a cubic polynomial. Good. Now, where x equals 1 plus I. This is a polynomial, and the number of pertinent roots it has, thus the number of values of I, are dictated by the Descartes rule of signs. What? Descartes rule of signs. There are many things here that we need to look at. The number of pertinent roots. What do I mean by pertinent? Meaning, there are only there are certain roots that are actually appropriate for this case. Uh, like what? For instance, would you agree that if one of the roots of this polynomial is negative negative 5, well, yeah, mathematically x could be negative 5 for a cubic polynomial. Well, what does that mean? X is negative 5, meaning I equals negative 6, right? Negative 5 equals 1 plus I equals negative 5 minus 1, I is negative 6. What in the world does an I, the internal rate of return being negative 600%, negative 6 or negative 600%, what does that mean? It has no meaning whatsoever, right? Even though the math tells you that negative 6 was one of the roots, yeah, it has no pertinence in this context. Similarly, recall that a polynomial could have complex roots, right? And if it does have complex roots, when the coefficients are all nice real numbers, when the coefficients are all real numbers, there is a rule. Um, if there is a complex root, something of the form x plus iy, then automatically x minus iy, its complex conjugate, should also be a root. Anyway, so the point is the roots of this polynomial, or even a bigger polynomial in a different case, could be complex. But then my question is a complex root pertinent in this case? No. Then we are saying I is a complex number. The interest rate is a complex number. Oh, damn. There is a little confusion. I is square root of negative 1, which shows up in complex numbers. I'm not talking about that I, right? So anyways, so a complex number value for the internal rate of return is meaningless. That's the point I'm trying to make. Good. So which ones are pertinent if that is the case? The only pertinent values for x are positive real roots, right? Positive real roots. And also, not only positive real roots, but because we we have expressed this uh, in terms of x, where x is 1 plus I. What if x turns out to be, say, 0.5? Hey, that's a positive number. Is that a pertinent value? No, x equals 0.5 makes I to be, x is 0.5, yeah, makes I to be negative 0.5. I cannot be negative. So even though x equals 0.5 is a positive root for this polynomial, that is not a pertinent root because I in that case turns out to be negative. So x must be positive and greater than or equal to 1. Only those roots we'd be looking for. Cool? Good. Positive roots that are bigger than 1, or if you're solving this in terms of I, positive roots where I is greater than 0, greater than or equal to 0. Those are the ones we're looking for. But is there a way to finding how many positive real roots a polynomial has? And that's where this guy, Descartes, the famous Rene Descartes, do you know philosophy? This guy, Rene Descartes, is the one who, from, um, what is that? How should I put it? The famous Cartesian coordinate system is based on Rene Descartes, right? And he's also in philosophy the guy who said, I think, therefore I am. Uh, Ergo cogito sum, meaning, hey, somebody asked him, what's reality? And he was like, what's reality? Hmm. For instance, are you real? Is the table here real? Is the chair real? Somebody asked. And he started thinking about it. And he said, I don't know if I can say anything is real, honestly speaking. However, I must be real. Why, Rene? And he goes, I am thinking. Am I not asking the question? Am I real? For me to be able to ask that question, am I real? I must exist, right? Now, it is entirely possible that I or my brain, which is doing the thinking, you extend it a little, could be a brain in a vat, right? So, however, whether it is a brain in a vat or what, that brain must exist for me to be able to think and ask the question. So that's ergo cogito sum. I think, therefore I am. Sorry for the detour, guys. Anyways, so this is the polynomial and the pattern dictated by. Okay, what in the world is this Descartes rule of science? The number of positive real roots of a polynomial, which is what we are interested in, are equal to the number of sign changes of the coefficients of the polynomial or differ from this number by an even number. Ooh, that's number of sign changes of the coefficients or differ from this number by an even number. I think that all that requires uh, lots of explanation. I'll do that in the next slide. But in our case, there is one sign change, right? If we apply this one, notice we have a negative p and negative a, so negative and negative, good. But then when we come to the very next term, it became positive. Aha, so there is a sign change from negative to positive. And then there is this, the last one is also a positive. So there is no sign change. So the only sign change occurred when we from between negative to positive from A1 to A2, right? So we, according to by Rene Descartes' rule of signs, we can be confident that there is only one positive real root. So in the previous case, where we did have numbers for P A1 and A2, A3, that single value that we got is perfectly fine. Okay, that's the idea. All right. So I thought, man, let me go ahead and clarify all of this rule of signs thing. I know it's a little math, but it doesn't hurt. So I chose to pick a polynomial, like on purpose. I wanted nice positive real roots. X minus 1 times x minus 2 times x minus 3 times x minus 4. If you set this equal to 0, would you agree the roots are 1, 2, 3, and 4, right? Or 4. And then when you multiply out, you get this polynomial. Okay. So now let's do this analysis, sign change, and so how many roots and all that. How many sign changes are occurring? Start with the coefficient of the leading coefficient, which is the coefficient of x to the 4. That's a positive 1. We don't care that it's a positive 1 or 2 or 5 or whatever. Positive. Good. The very next one is a negative 10. Aha. So there is a change. One change from positive to negative. But then there's another change here. So that makes it two changes. Again another change. That's a three changes. And again a change. So four changes. So there are four changes of sign in this particular polynomial, right? Good. According to the rule of signs, if there are four sign changes, there should be four roots, four positive real roots, number of positive roots. And if you plot this, yeah, duh, right? 1, 2, 3, 4. Notice how this polynomial is intersecting the x-axis at x equals 1, 2, 3, and 4, right? Yeah, we know that. So there are four sign changes and there are four positive real roots. Cool. All right. Which are 1, 2, 3, 4. Now, I picked another polynomial where two of these roots would be 1 and 2. Those are the positive roots. But the other two roots are negative ones, negative 3 and negative 4. So what happens in this case? How does the Descartes rule of sign work in this case? Let's see. Sign changes. Positive, positive, negative. So one sign change, negative, positive. So one sign change here and another sign change here. So there are two sign changes, right? According to this, how many should we have? We should have two positive real roots, right? Based on the figure, if you can see, there are two negative roots here, but the positive roots are 1 and 2. So there are two positive roots, which happen to be positive 1 and positive 2. Cool. So you're getting a hang of this sign changes and the number of positive roots? Good. Let's pick another one. X minus 1 times x minus 2 times x minus 3i and x plus 3i. Aha, so the roots are 1, 2, and these complex conjugates, 3i and negative 3i. But notice, this polynomial has all nice real coefficients. Even though the roots are complex, the polynomial itself has real coefficients. That can and will happen. Okay, good. Now let's do the analysis. How many sign changes? Positive to negative, 1, 2, 3, 4. There are four sign changes, right? So how many positive roots this should have? If there are four sign changes, if there are four sign changes, there must be four positive roots, man. Uh-oh. There are only two. Stupid Rene Descartes, right? He's wrong. No, he's not. Mathematicians for centuries couldn't be using this and somehow it is wrong. Some mere mortal like me could show that he is wrong. No, no, no. This is what Descartes was completely aware of. And he said the number of positive real roots of a polynomial are equal to the number of sign changes, kind of like what happened in the previous two problems of the coefficients, or differ from this number by an even number. What does that mean? If you see four sign changes, you could have four positive real roots or 4 minus 2, right? The even number 2. 4 minus 2, that is, it may have two positive roots, which is exactly what the case is. Or guess what? It could have even 0. 4 minus 4, the other bigger even number, could have 0 positive real roots. What? Yeah, you can clearly see. What if instead of x minus 1, I had x minus I and times x plus I. Then that would have been x square plus 1, and this would be x square plus 9. X square plus 1 times x square plus 9, you will see that, we can multiply, it multiplies out, and it would have zero roots, zero positive roots. Cool, zero positive real roots. Alrighty. So that's something that I wanted to show. Positive roots, which are 1 and 2 in this case. Cool. We need to emphasize all of this because in our case, what we are studying about internal rates, we could in fact have multiple internal rates of return, multiple IRRs. That is entirely possible. So how do we treat that is something we're going to learn. A firm is considering the purchase of flow valves that will reduce annual operating costs by $10,000 per year for the next 12 years. The firm's minimum attractive rate of return is 7% per year. Using an internal rate of return approach, determine the maximum amount the firm should be willing to pay for the valves. We know they're going to get 10,000 every year for next 12 years. So what should they invest? What should P equal? So that use the internal rate of return approach and say what P is. Okay. We will calculate the maximum amount to be invested by using IRR equals minimum attractive rate of return. Okay. And so we'll say minus P times 1 plus this thing. We should. I need to clarify something, right? Why is it that when we use minimum attractive rate of return, we see that we can find the maximum amount to invest? Does that make any sense to you? Okay. I think it should, because anything beyond that, the P value or the F future worth value or the present worth value will actually go negative, right? That's the idea. The investment would be so high, which would be much bigger, that, in other words, yeah, just look at this one. If P were to be bigger than what we are about to calculate, it turns out for that to be true, this would be the I factor, the IRR would be less than 0.07. So that's why the maximum value, maximum amount to be invested, to do that, we set the IRR equals the minimum attractive rate of return. And then simple math, and that turns out to be $79,426.86. So this is the maximum you can invest. Cool. Just for your own sake, take this to be this 0.07 to be I. You don't know it. Change this P to 50,000. See what I will turn out to be, right? That I will turn out to be greater than 0.07. So that means, yeah, investing less than this 79,000, yeah, by all means, if you're still getting the same $10,000 per year for the next 12 years, if by investing less, of course you go for it. And automatically it turns out that the internal rate of return that you calculate would be bigger than this minimum attractive rate of return in that case. However, go ahead and calculate by making P to be, say, 100,000 and leave this 0.07 as an unknown I and figure out I. that will turn out to be less than minimum attractive rate of return. Okay, that's the whole idea. All right. I like this problem. It's a very conceptual problem. Your FE exam, oh boy, they dig these kinds of questions because these are conceptual things. If the interest rate at B is 20%, then which of the following best describes the analysis of the investment? So they have given us a graph of present worth and interest rate. And then they are saying, hey, according to this, which which exactly describes, for instance, A, the internal rate of return of the investment is less than 20%. Could you say that by looking at this figure? Or B, internal rate of return of the investment is equal to 20%, or greater than 20%, or none of the above? I don't know, man. I can't tell, right? I like these kind of questions. What? The interest rate at B is 20%. Notice on the abscissa, that is x-axis, you have interest rate, and on the ordinate, we have the present worth, right? Cool. The interest rate at B is 20%. That makes perfect sense. So this is a abscissa value. Then the number here is 20% or 0.02. Cool. What are they asking? Which the IRR of the investment is less than 20%. Huh. So the question from the figure, which point gives a measure of the IRR? What? Does A tell you anything about the internal rate of return? Or C? Or B? Or E or D? Which point? Right? Now check this out. How do we find this IRR, internal rate of return? We set the present worth equals 0 or future worth or annual worth, one of them, equal to 0. What does this graph tell us? It says this present worth is a function of the interest rate. As interest rate changes, the present worth changes, right? So if the interest rate is 0, the present worth is whatever this y value here is, right? That A point, the y value or the ordinate value of this point A tells you what the present worth is. And as I keeps increasing, at some point, for instance, the present worth becomes 0. Now, isn't that what we are looking for? So on the graph, IRR is this particular abscissa value, x value. Cool. So now I hope you get an idea. Since the present worth is a function of the interest rate, and since IRR is the interest rate at which present worth is 0, point E gives you the measure of IRR. Since the abscissa of E is greater than that of B, right, the x value of E is definitely bigger than that of B. This is 20%, and looks like E is a bigger x value. So the internal rate of return must be bigger than 20%. Cool. That's a good problem. Very nice conceptual problem. And let's see. A design change will cost $6,000 and will result in annual savings of $1,000 per year for the 6-year life of the project. A cost of $2,000 will be avoided at the end of the project as a result of the change. Minimum, what is the internal rate of return? What is the decision rule? Should the firm, okay, whatever. Okay, setting the future worth to be 0. Oh yeah. Oh, okay. Yeah, I like this problem. Let's go over it. Future worth will cost $6,000. So in the beginning, right? So negative 6,000. And then projecting it to the future, the t equals 6, did this. And then annual savings of $1,000. That's a plus 1,000. And that happens every year for the 6-year life. So using that $1,000, finding the future value at t equals 6, and then a cost of $2,000 will be avoided at the end of the project as a result of the change. So we'll add that as a positive because you wouldn't have to shell out the 2,000 at t equals 6, which normally you would. So plus 2,000 equals 0, right? And the minimum attractive rate of return in this case is 8%. Are they saying I is 8%? No, they're not, right? We need to figure out what I is. Cool. All right, what is the internal rate of return of this investment? So what is that I that makes this future worth equal 0? That's what we need to find. So how do we do this? Solving the seventh degree polynomial. And I put a question mark. Seventh degree polynomial? What? I thought I see only 1 plus I to the 6, man. Why are you saying this is a seventh degree polynomial? So I need to answer that question, and I certainly will. Solving the seventh degree polynomial for I is not easy. Not easy. I'm sure you agree with me. So we'll use trial and error method or some software. I think I'd rather go and use some software for this. However, even though we are saying that, we should know how many positive real roots this has. Right? It's always a good idea to do some math also. Because if you somehow think there is only one root, we know a sixth degree polynomial could potentially have 6 roots. All 6 could be nice and positive. So did you eliminate that as a possibility, or did you go, hey, I punched into the calculator, man, and I got some number, ta-da, that's my internal rate of return. Whoa, whoa, whoa. See, this is the difference between technicians and us engineers. We do a little more. We can do math, right? All right. So I said, let's do some Rene Descartes rule of signs and figure out. Even though we're not going to find the exact value by doing this, we're just going to assess how many positive real roots can I expect is the idea. Okay. All right, so you can see you can divide throughout by 1,000, and so that makes it this into a slightly simpler equation, simpler looking equation. But I still need to answer the question of, is that a seventh degree polynomial? Let's see. Then, would you agree? I can multiply throughout by I, both sides by I, because there's an I in the denominator. So that becomes minus 6i times 1 plus I to the 6, and you will have 1 plus I to the 6 minus 1, and plus we are multiplying this by 2, so it becomes 2i, right? So same polynomial written in a different way, but we are multiplying multiplying the whole thing by I. We can do that, right? We can multiply both sides of an equation by the same number, right? Be careful. Don't just jump and say, yeah, man. What if the quantity that you're multiplying by happens to be 0? Can you multiply by 0? The answer is no, you cannot multiply both sides by 0. We are multiplying by I. So we have to keep in mind to check whether by some chance I turned out to be 0 as one of the solutions. If that is the case, then that solution is not valid because we promised that I will not equal 0 when we multiplied throughout by I. Cool. All right. What else? So let's do this. Let x equal 1 plus I, and that means I would be x minus 1, right? Subtracted 1 from both sides. So let's remove i's and just make it x in terms of x. So what should we do? Minus 6 times, instead of I have a times x minus 1. And instead of 1 plus I to the 6, I have a x to the 6, right? Plus x to the 6 minus 1 plus 2 times x minus 1. And so this, that's a nice looking polynomial. Good, let's ask ourselves. Sign changes. How many positive roots could it potentially have? There's a negative to positive, one sign change, positive to positive, zero. So there is still negative, still one change, but again, positive to negative. So there are two changes. Aha. So this has two things, two changes. So potentially could have two positive real roots. Hmm, good. So let's be careful. Don't just look for only one value. And when I plotted this on GeoGebra, I got x to be this polynomial, which is 1 plus I, to be 1 or 1.0745. So there were, in fact, two positive values, positive real roots of this polynomial, 1 and 1.0745. That's for x. Oh, so what is I? I equals 0 or 0.0745. Aha, so I equals 0 turned out to be one of the values that actually satisfies this equation. Uh, really? I equals 0 satisfies this one? Yeah, but then we cannot take that I equals 0 as a possible solution, because when we solved this, we said we won't let I equal 0. Right? That's a promise we made. So even though this looks like a solution, I equals 0, it is actually not a solution. Cool. And so the only valid solution is this 0.0745. So IRR is 7.45%. Okay. The thing is, man, should you go this mathematical? Right? I'm just an engineer. No, I'm telling you, learning these kinds of mathematical background things is definitely a good idea, because quite possibly in your workplace, wherever you're working, they may be bumping into some issue. Everything is working fine and dandy for quite some time, but then there may be one problem which is baffling everybody, and they're all just pulling their hair out. Man, what's happening here? I can't tell what's going on. I just punched it. And that's when, if you just dig deeper and do a mathematical analysis like how we did for this one, then you can come back and say, aha, that is the mistake you made. And based on mathematics, right? Everybody will go, attaboy, where'd you graduate from? Right? Okay. Ladies and gentlemen, oh, by the way, yeah, what is the decision rule for the attractiveness, single attract alternative case? So the attractiveness of an investment is based on the following. If the internal rate of return is bigger than the minimum attractive rate of return, choose to invest. Otherwise, don't. Right? So what happened? What is the internal rate we got? 7.45. What's the minimum attractive rate of return? 8. Oh no. This stupid project gives us a rate of return which is less than our minimum attractive rate of return. No, we are not going to do the project. That's the whole idea. Cool? Amigos y amigas, adios.